Okay, so hello everyone. I hope you had a great weekend. Just a short announcement, like on organizational side. This week we're gonna be looking into dividing the fellows into groups for better collaboration. And yeah, we kind of finished with the block getting into Sumo code base. This Wednesday, we're gonna have first office hours with Sumo team, and we are starting with our retreat sessions. And I'm very excited to have our first guest speaker, who is the head of security in Kalos, rkm0959. Welcome.
Hello, everyone.
And yeah,
Oh,
we
okay.
try to
Yeah.
sorry, we try to run like this presentation like with a logical break. So feel free to ask your questions in chat, like, and raise your hands. And yeah, I guess we would have some breaks to take questions. The mic is yours.
Okay. Okay. Thanks for having me. I'm very honored to speak about this topic in front of so many talented people. So thanks for the introduction as well. So today I'll be talking about like a brief overview slash survey slash my opinions on ZKP security. To like give you some brief digest about my experiences with security and ZKP security in general. So I've been working at Kalos as a security researcher starting from 2022. And for some ZKP related auditing, I have audited Scroll ZKVM, some parts of Scroll ZKVM circuits and Axiom's circuits. This was done with collaboration with Zelic. And I also audited Succinct Labs prover. So it was like Stark related prover called Curda. This is open sourced. And for some other security related stuff, we placed the Kalos with some external collaborators, placed second place in the 2023 Paradigm CTF. And I also played some Web2 related cryptography site CTFs with a team called SuperGuesser, and we placed like third overall in 2021. And I also have some like math Olympiad slash competitive programming background. So Scroll, Axiom, Succinct Labs, all very strong teams. The Succinct Labs audit isn't public yet, but it will be public soon, hopefully. So I hope that you all can see some like very cool bugs or findings from that audit report. So anyways, so the outline of this talk is so for the outline, the target audience for this talk is like soon-to-be auditors with very strong, well, let's say just strong security background and a high-level understanding of ZKP and some good understanding of ZKP-related programming. So you know how to read Halo 2 source code or Sarkim source code, and who wants to like expand knowledge into this new field of ZKP security. And the main goal for this talk is to discuss, for first of all, this since the like previous title of this talk was Taxonomy of ZKP Vulnerabilities. The main topic here will be to discuss various attack vectors in ZKP security. With I didn't bring a lot of examples, but mainly just discussing attack vectors. And the another point I would like to talk about is discuss why like these attack vectors actually exist. So I'll be talking about the fundamental reason of why such attack vectors exist. And this would lead to us discussing something that's been like talked about quite a lot in, I don't know, like security Twitter or ZKP Twitter or something like that, which is like how much math you need to do like ZKP related, security. So we'll be discussing about that. And the key question here, yeah, as I mentioned earlier, the key question here that I would like to like try to answer is how much math do we actually need? So a lot of ZKP like auditing slash security related talks start with this some sort of a, I don't know, programming, the development stack. And this is taken from my Ethereum Soul talk back in like June of last year. So basically, when you're developing a ZKP related like projects, what you do is you start with some sort of a specification of what the application is trying to do. So if you have like, let's say, a proof of solvency protocol like Summa, so you figure out like what you want to do, like the desired specifications of the application. So you figure out like what things you need to check. Like for example, if you're I don't know, you have to sum the amount of like assets you have and stuff like that. So you figure out what to check. So you have like this some sort of form of a written spec, so that at that point you would have this like list of raw constraints to check. But since this is a ZKP thing, you have to feed those constraints into you have to spoon feed them into like this language, this complex language, which only allows like additions and multiplications and lookups and so on. So you have to digest the constraints into a ZKP friendly manner, which is a process called like implementing the circuits. And at that point, you have like this logic that so-called quote unquote arithmetizes the constraints into like for example R1CS or Plonkish form, and a logic that generates the quote unquote witnesses so that the final cryptographical backend, which is like magical stuff, can actually generate the proofs and the verifiers related to it. So that's the whole like stack of a ZKP application. So basically what the Ethereum Sol talk was about, to like give a brief summary, was that vulnerabilities happen in all these three parts. So for example, to get the most complicated one out of the way, so consider the cryptography magic part. What could happen to cause a vulnerability is that the cryptographical backend that like generates the proofs and witnesses and all the verifiers and all that could be like flawed. So maybe like the MSM code is flawed, the FFT code is flawed, like the Fry verifier is flawed, and it does not have like, I don't know, zero knowledge or something like that. But those parts are like very like difficult. Like you have to audit the like very, very deep ends of the ZKP like programming stack in order to find those bugs. Like this is in comparison to smart contract security, this will be something like finding a bug in a Solidity compiler. So this is the part that not I don't know, like it's pretty in the deep end. So we don't really need to talk too much into it. So the main part when we are talking about the ZKP security is the first two. So on the first two, the first part is as we mentioned earlier, figuring out what to check. So indeed, like one of the main attack vectors that we commonly see in ZKP security is that like you simply have made a mistake at the specification level. So basically, you have to like know like what the application is actually about in order to audit it. So like this isn't really related to ZKP in general. So for example, if you're auditing a ZK EVM, which is a ZKP like implementation of the EVM, you're implementing the state transitions into a ZKP friendly manner. So if you want to audit that, you probably need to know the EVM very well. And similarly, if you're, let's say, auditing a ZKP implementation of a signature scheme, let's say EDDSA, then you will need to know EDDSA very well. So for example, like how do you securely verify EDDSA? And one interesting thing that comes out of this is that if you're using recursive snarks, so basically what like this attack vector means is that you have to know like what you actually have to verify very well in order to like audit the like constraints digested into a ZKP friendly form. So what could happen is that if you're using recursive snarks, you have to verify the snark inside a prover. So if you don't know like what you actually have to do when you're doing a recursive snark, you're basically making a mistake at a specification level. So the case in point being like you actually have to know like what type of thing you're actually auditing. Uh yeah, I think I made enough sense there. And that's actually very common. Also important is that you have to make a clear distinguishment of like what's verified in circuit and what's verified outside circuit. So for example, what's verified outside circuit might be something like Ethereum L1 smart contract. For example, like if you're doing Tornado Cash related stuff, the fundamental thing that the L1 verifier on the smart contract has to check is that a single nullifier cannot be used twice. That's supposed to be verified on chain. That's not going to, if there's a vulnerability related to like a double spend of a nullifier, that's probably going to be on chain. So you have to make a clear distinguishment and like a clear view of what is verified inside the circuit and what is verified outside the circuit, and whether or not these two constraints in circuit and out of the circuit combined is sufficient to make a secure protocol. So obviously, integrating different code bases into a single project is always a delicate process. Like if you have like two parts of a project and one team verifies the first part and second team verifies the second part, there's going to be like issues related to like some parts of first portion and some parts of second portion being mixed together to create a like very complicated bug. So there's always those integration issues. So you have to be very careful about what the specifications are. And this is like one of the parts where like people ask about like needing a lot of cryptography. There's like you have to be like very careful about like your statements regarding how much math you need. For example, like if you're auditing a ECDSA related stuff, you obviously have to know like elliptic curves very well. But if you're auditing like not something that's like not related to like elliptic curves at all, then you don't really need to know elliptic curves that deeply, in my opinion. So that's one like clear distinguishment I want to make, which will be like mentioned later as well. So if you know, so do you have any questions here? This is like the part one. So this clears the first part, figuring out what to check part. So does anybody have any questions?
I think all good
Okay.
so far.
So now we figured out that the list of checks we have to do, so list of constraints we have to make are like finished. So we know we got the specifications right. And now the problem is that you have to like translate those constraints into a circuit friendly one. So the biggest part here is that the biggest differences from your regular programming and ZKP related programming is that first, as we know, all witnesses live in a finite field. Let's say FP. Well, it might be like some binary field starting with Venus, but let's just say finite field for now. And there is a limited set of constraints and tricks, and some of them are very cryptographic. And also, if you're doing Plonkish, such as in Halo 2, the witnesses are written in a fixed rectangular board. By a fixed rectangular board, I mean that like the number of like columns and rows are fixed. And since if you like know on the underground, the back end of Plonk, you would realize that in the end, every single like constraints are going to be translated into a like a polynomial equivalent, some kind of like polynomial related statements, and those statements are all fixed in advance. So since the verifier has to like know like how the circuit is designed in the first place, you can't like have like a variable number of like cells or something like that. So while the witnesses itself can be different from like instances to instances, the board itself should be fixed. So these three things are the main differences between the regular programming and ZKP programming, or at least for now. So the first part is that we are in a finite field. So if we're in FP with P prime, with P being a prime, the first major thing that this leads to is that there are overflows and underflows. For example, like P is equal to 0 in FP. So there's that. And the another thing is that P is not like overflows and underflows, like we are like, overflows and underflows are not a new thing. Like it happens all the time. If we are in like Uint 64, either in like I don't know C++ or Rust or something, like we are already aware that overflows and underflows exist. The main issue that makes it kind of like confusing is that P is not like a power of 2, and this leads to like double spending ideas when we are like mixing it with the Ethereum L1. So we'll see that later. The first thing is that overflows and underflows exist, as we mentioned. So the main issue here is that there is a discrepancy between equality over the integers, which is what we usually desire. For example, if I don't know, like if I pay you like a Ethereum and you already have B Ethereum, then your final balance would be A plus B Ethereum, and that the result being A plus B is a equality over the integers. But in ZKP, since we are all living in the finite field FP, what we usually can test easily is equality over FP, which is different from equality over the integers Z. So for example, let's say that we want to test A modular Q is equal to R. The classic way to do this is you bring out, you bring out a witness B, and you check that A is equal to B times Q plus R, and this is computed in the field, so this is computed in FP, and you check that R is between 0 and Q, where R and Q are considered in Z, the set of integers, and you claim that you have to additionally check that A and B times Q plus R is between 0 and P when they are computed in the integers. So if you missed this last check, what could happen is that A and B times Q plus R are equal over the field, but they are different when considered over the integers. And in that case, you could claim that this R value is something different than what we actually intended to be. And this would lead to a soundness bug. And of course, because we have to prove that A and B times Q plus R is below P, and we have to consider this when we're computing over the integers, it makes it difficult because now you have to simulate integer arithmetic when we are only allowed limbs that live over FP, which is a field. So that's what makes this thing very not easy and hassly. Some other methods for an attack is using the fact that a value x and value x plus p are the same when we are considering in the finite field FP. And however, in the L1, let's say out of circuit, these two values are different because they're clearly different. So you can use this trick on nullifiers to cause a double spending. So what would happen is that for first proof, you say that the nullifier is equal to x, and for the second proof, you say that the nullifier is equal to x plus p. Since these two values are same in circuit, the both proofs will successfully verify on chain. But if the L1 does not check that this nullifier value is less than p, both x and x plus p, both being in U-56 range, will check. It will pass all the checks, and this would lead to a double spending. And this has been a common bug in many projects. And this, there are plenty of examples in the popular ZK bug tractor repository. And so this concludes the issues which come from the fact that we are in FP instead of a usual U-56 or even better integers. So that's the part one of this this thing. And does anybody have questions? Wait, yeah, we're done with this part. Does anyone have questions?
I think it's clear.
Okay, yeah. And now we have the second part, which is that we have a very limited set of constraints and tricks. So the list of such tricks is first the very basic addition and multiplication over a field. The second being lookup arguments, possibly being dynamic, quote unquote dynamic, which means that the table we're looking up to is not a fixed column, but rather an unadvised column. And there's also lookup arguments that's being done on vector value things. So you're looking up a vector instead of a single column. And there's also randomness sampling via Shamir. And in Halo 2, this is represented as phases, like first phase, second phase, and so on. And while this is not, while the last one, offline memory checking algorithms, is not in Halo 2 as far as I know, but it's a new primitive that could definitely be helpful later on and could be definitely implemented in some other prover or other DSL/library. So that's another one. So basically, these lead to the following four category of vulnerabilities. So the first one is assigned but not constrained type of vulnerabilities, and the second is just basically additional missing constraints. Third one being incorrect handling of assumptions and their specifications, and the final one being just incorrect usage of cryptographic tricks. So let's go over them one by one. So the first thing is assigned not constrained. So So the main reason why these bugs happen is that the constraint system is very limited. Like the type of constraints we can use is very limited. So these force us to assign variables by an out of circuit computation and then just constrain them afterwards. So for example, so what I mean by this is that consider that you have a 64-bit value A, and you want to bitwise decompose bitwise decomposition them into like B0 to B63. So you want to like find the B values that satisfy this thing. What would be very like nice if it was possible is that if you could like just compute BI straightforwardly in circuit, it would be very easy. Like you know, it would make us write the code with less mistakes. But unfortunately, it isn't that easy to do it via by direct constraints. So what we actually do is you compute the BIs out of circuit first, and then you assign them as witnesses, and then constrain that A is the sum of BIs, as a bit vector, and then BIs are all bits by multiplying BI and BI minus one, and then forcing them to be equal to 0. So as you can see, you can't compute BI directly in circuit. You have to assign them first, and then place a constraint that forces these BIs to be correct. So this kind of this is an example that shows why you need off the circuit computations. But unfortunately for us, this fact leaves us with a lot of vectors, a lot of possible I don't know, how should I say this? It opens us a lot of possibilities for us to make a mistake. So for example, like because of this fact, Circum now has to support like in language assignment without constraints. So like for example, the left one here is the correct implementation of is0. So you see that inv is computed out of circuit, and this is needed in order to like actually compute inv. But since now there is this like arrow with a single dash on it, there's an arrow with a single dash on it. Now one can like forget that this actually doesn't place a constraint, and then just write a is0 template like it's on the right side of things, like this on the right here. And this is obviously not a correct way to do it because it only assigns temp, but it doesn't constrain temp at all. So one needs to be very careful about how the library handles this thing. So for example, here's another possible mistake. So consider a copy constraint in Halo 2. What the correct way to do this is just place a copy constraint on it. So you just connect two cells and force them to be equal. An incorrect way to do this is read the witness value of a single cell and then just assign it to the other. And this could be this makes us this is obviously a mistake because you just copy the witnesses, but you never like constrain that the two values at the two cells have to be the equal values. So that's one possible vector. And the other vector is that you can just like simply have like additional missing constraints while translating a, a constraint into a ZKP friendly one. So for example, like if you just know that you have to constrain this this equation, say let's R is equal to the Boolean value of A is less than equal to B. If we were like doing this computation out of on just like a solidity thing, then you could just write this and be done with it. But now since like ZKP doesn't support like A is less than equal to B, A is less than equal to B, you have to like constrain this by yourself. And uh, in ZKP, the usual trick here is that you first do a range check. You do a bit length check on A and B. Say that A and B is between 0 and 2 to the power of n. And you write 2 to the power of n plus b minus a is equal to 2 to the power of n times r plus c, where r is range checked to be a bit, and c is range checked to be within 0 and 2 to the power of n. So obviously this conversion is not trivial. Like it isn't difficult, but it's not trivial. And while translating a constraint that it has to be there into a constraint that you have to check that this is equal to this, and this translation into ZKP friendly thing satisfies both, completeness and soundness. It's very untrivial, not trivial. So this conversion is very tricky, and such conversion opens up many vectors for mistakes. And another very common mistake that I found over my experiences is that, for example, the circuit above here, uh, this method of translating a is less than equal to b into a more CKP friendly one. This trick requires you to know that a and b is between 0 and 2 to the power of n. So this is an assumption on the circuit itself, and this is very common. And for example, to give a counterexample on why this assumption is needed, you could consider cases like a is equal to p minus 1, b is equal to 0, and r is equal to 1. For example, if a is equal to p minus 1 and b is 0, this would be 2 to the power of n plus 1. So you could say r is 1 and c is 1. But so r is 1, but you see that a is p minus 1 and b is 0. So this is actually false. So r actually had to be 0. So this is a case that shows the idea is not sound when this assumption is removed. So in some cases, so what mistakes are possible is that people will use like this trick, but without checking that A and B are within this range. And as I mentioned before, this leads to like a break of soundness. So why does this mistake happen? Well, the main reason for that is that like if we were in a like Ethereum L1, unless you're like gas optimizing like crazy, we could just check this kind of constraints everywhere. Like you could just, if this is a function, if this is a chip, and let's just say if this is a quote unquote chip, but we're in like Ethereum L1, what you can do is that you could just check that A and B are between 0 and 2 to the power of n every single time, and it would not cost us that much. But unfortunately, since we are in ZKP and like checking that A and B are within n bits is not a trivial operation, uh not a trivial operation, and it cost us a lot because you have to like bitwise decompose again. Because these constraints are very expensive and performance optimization is very important in ZKP, you can't afford many code bases cannot afford to do range checks over and over on a single value, let's say. So what they would try to do is they would range check a single value once, and then starting from that point, it would use chips that assume that this value is already range checked. But if you don't perform a range check in advance, there could be a mistake on handling the assumptions, and then it would lead to a full break of soundness. So documentations are very important to prevent this. So if you have a circuit or a chip that requires a variable to be within range, it is very important to document that fact, so that nobody makes a mistake. For example, like using that chip while your variables are not even range checked in advance. So it is very important to watch out for this. And even if like there's no like soundness issues that are made by the team, it's also very just important to like just advise them to document their codes properly. Uh, and the harder part of the you know of vulnerabilities of this kind is the usage of incorrect cryptographic tricks. So as I mentioned, there are like lookup arguments, Fiat mirror tricks, and offline memory checking. And these each of them have their own rules that need to be like verified when you're auditing the code base. So let's talk about the lookup arguments. And so for dynamic lookups, where the lookup table is actually an advice column, you need to check that the entire lookup column is constrained appropriately. So, for example, this was like actually a common bug that was found on like I think it was scroll. So what could happen is that if you have a advice column that's being used as a table, if a single entry or single row of that column is under constraint, let's say like it's allowed to be like every single value, what could happen is that one can fill that unconstrained entry as whatever you want it to be, and then perform lookups on it. So you could just break the entire lookup. So let's just say that this dynamic column is supposed to be on specifications, supposed to be like filled with like zeros, ones, and twos. But if the circuit forgets to constrain one single entry uh, as like something inside 0, 1, and 2, then you could fill it with 5 and then claim that 5 is within 0, 1, and 2, and that's already broken. So you have to be very careful to avoid that. And for vector lookups, it's very important to combine the vectors into a single value with Fiat-Shamir randomness and not some fixed number. This is also like explained in the proof of how vector lookups work. If you read the full Plonkoff paper or plookup paper, whichever paper that handles with lookups, they always tell you that vector lookups should be done by combining like oh yeah, go ahead, Ali.
Ali, you can ask.
Yeah.
By combining here, do you mean some sort of commitment to the entire table?
Okay, so the way vector lookups work is that you combine, I'll just write it on the chat. You combine this vector into like it differs from like lookups to lookups, but the common trick in vector lookups is that you transform this vector a1 to an into a single element, like this uh by sampling some gamma, which should be random. And possible mistake that one can make is if you use fixed gamma, like let's say just gamma equals 1, then it breaks the vector lookup. The correct way here is to use gamma as a like hash of like entire board, entire first space board. And this is the correct way to do a Fiat-Shamir on it. So you have to be very careful that if the let's say if the like code base itself, if the internals of the vector lookup is not exposed to you, then you don't really need to be you don't really need to care too much about it, because like it's all done in the back end. But if you're auditing a code that like actually does the vector lookup like explicitly, then you have to be very careful that the elements inside the vector are combined with sufficient randomness.
I think this is commonly referred to as linear combination, right?
Yeah, linear combination is also correct. Yeah.
It's it comes up a lot in various places,
Yeah, right.
in folding in many places. So I think this is something that fellows expect to see a lot. This idea of creating a linear combination as a way to commit to something so that the proofer
Right.
cannot beat and switch here.
Yeah. And it's important that if you're going to commit to an entire thing, I mean, this comes up later as well, because we're going to talk about Fiat-Shamir the very next slide. But yes, it's very important to combine elements with sufficient randomness if you're going to commit to an entire vector. Gamma is that's actually not that relevant here. You just need gamma to be like Fiat-Shamir random. So for example, gamma should like be a hash of something and a1 to an. So at that point, it's not reversible. And if you want to know about like why is this not reversible, it's because of the random oracle model, but that's going way too far. But yeah. Okay, so moving on. So like immediately after we were talking about vector lookups, we were talking about Fiesch-Shamir, so it's like all perfect. So in Halo 2, a phase exists to handle multiple rounds and their relevant randomness. So what would happen is that you have this columns that are in first phase, and you combine all those things in first phase and then hash it to create a randomness that's going to be used for second phase things. So even if like explicit phases are not used, implicit ones are definitely possible. So a good intuitive understanding of Fiesch-Shamir is very important. And if you want to know a little bit more about this, you could also like read a little bit about the random oracle model. But all in all, if you're auditing, you have to like a full cryptographic understanding is not needed, but you have to have a very good intuitive understanding of it in order to like audit protocols that exposes phases very explicitly. So for example, here's one very common example. So a random linear combination application is to prove that C is the concatenation of A and B, where A, B, C are strings of fixed length, NA, NB, and NC, where NC is the sum of NA and NB. By the way, this is taken from the Axioms HagMD, so shout out to them. You can check that RLC of A times gamma to the power of NB plus RLC of B is actually equal to RLC of C, where we define the RLC as with randomness gamma, like this polynomial value. So this is a very common trick, but one thing that's very important is that gamma should be sampled from a Fiesch-Shamir operation. So gamma should be hash with a preimage that includes A, B, C somehow to prevent like incorrect Fiesch-Shamir attacks. So to get an intuitive idea of like how we attack weak Fiesch-Shamir. So what would happen is that, for example, if let's say gamma is taken to gamma is actually computed as a hash of A and B, what you can do is, for example, you fix A and B first. This would fix gamma because we just said that gamma is computed from A and B. So what would happen is that you fix A, B, and gamma, and then you just fuzz around and like find a value of C such that the RLC of C is equal to this fixed value. And this C value does not have to be like a concat of A and B because you know gamma in advance. So the idea of like Fiesch-Shamir to explain it briefly is that if you compute gamma as a hash of A, B, and C, like all of them at once, then like changing C would completely change gamma because gamma is a hash of A, B, and C. So you can't do like such tricks. You can't like fix A and B, I don't know, fix A and B, and then like try something with different C and pray that like this equation holds, because changing C a little bit would just completely change up gamma. So yes, that's correct. So to like get a like complete understanding of like the stuff I talked about just right now, it would need you to like get a good intuition. So you would need a good intuition on Fiesch-Shamir, and if you like theoretical things, maybe Schwarz-Zipf lemma, it would be very helpful on your understanding on like why things are sound. And if you're going to go very deep and like analyze how secure, like as in terms of security bits, amount of security bits you have on a protocol, bits of security you have on a protocol, then it's very helpful for you to like know and understand Schwarz-Zipf lemma as well. And if you need a proof of concept with a higher severity, this is pretty optional, but a knowledge of lattice attacks is pretty recommended here. There's a talk given by Sempriti from Zelik on this matter. I'll like leave a link to you. It's in the Prog Crypto lectures. Like it was on anatomy of ZK VM exploit. I think it's on YouTube, and it's done by Sempriti, who worked on the scroll ZK VM with me, and it's a good talk, so you should go check it out. So anyways, are there any questions here? This one's the probably most tricky one in the ZK vulnerability landscape, probably. Understanding Fiesch-Shamir.
I think we can go.
The idea here,
Yeah.
The idea here is that weak randomness can allow a malicious prover to uh, to prove something that is incorrect. Like it could lead to a soundness, or if they
Right.
have some room to choose what that randomness is. So um, um, so yeah, randomness is the common factor between Fiat-Shamir and things like the Schwarzschild, basically. That's
Right.
basically the common point that you're trying to make here, right?
Yeah, indeed. Yeah, so in order to sample randomness correctly, you must not leave any room for the attacker to like, fix something and then fuzz around something else. And to do that, the Fiat-Shamir heuristic tells you that you should hash the entire transcript, hash everything you can pre-commit in advance. So which in here, in this case, it's both A, B, and C. And yeah, such as Fiat-Shamir attacks. And on offline memory checking, this isn't really common yet, but basically what it allows you to do, so to give a brief example, is it allows you to add and read tuples of the array name, the array index, the array writing time, the array value, and the multiplicity of read and write. And it claims that all values that are added are read at some point. And for example, so some potential issues that could arise in this kind of primitive is that, for example, if you like perform in order, this is a little bit confusing, but basically you read at index 1 at time t1, you write value v1 with multiplicity 1, and you read at index 1 at time t2 at value v2 with multiplicity 1, and you do that with t3 v3 and t4 v4. And if you do this in order, the like intuition you get from this code is that t1 and v1 and t2 and v2 as tuples are equal, and so are 3 and 4. But in reality, if you write out the constraints that correspond to this series of actions, the constraints you actually place is that the added tuples as a set and the read tuples as a set are equal. So it could lead to some soundness errors, but to be honest, like I haven't really seen actual like real world vulnerability that relates to this. So and plus there's not really a fixed spec, a, a single fixed spec for this technique. So it depends on the code base, but you should be aware of the cryptographic internals if you're auditing something that's related to like actual implementations of offline memory checking. And moving on to the fixed rectangular board. So in Plonkish, the witnesses are, as I mentioned earlier, are organized on a fixed rectangular board. And this leads to two things. First, it leads to the incorrect handling of variable length objects. And it also leads to incorrect handling of boundary/transition constraints. So let's move on to those two. So first of all, since the board is fixed and although like the polynomial equations and stuff like that are already fixed, you can't deal with variable length arrays with variable number of witnesses. So the usual trick here is to have a array of witnesses that are fixed length, which is of max length. So this allows you to deal. So if a primitive allows you to deal with, let's say, a variable length array with maximum length 50, what you do is you just assign 50 50 like witnesses, and then you just assign a variable for its actual length. And the main issues that usually arise with these variable length objects is that by using like prefix or suffix zeros, one could have, let's say, the RLC of A and RLC of B being equal, but A and B are different because they have like prepended or appended zeros at the beginning or the end, depending on like the endianness of the RLC. And this could lead to, like, for example, a program thinking a byte array like 5 and byte array 50 to be equal. And depending on the application, that could lead to some serious bugs. And the second one here is the distinguishment of boundary and transition constraints. So with the rectangular structure in Plonkish, a very common technique is to have a boundary constraint, which is basically conditioning a fixed row, a given row, and a transition constraint, which is conditioning between two, for example, let's say two consecutive rows. And for each region you place on Halo 2, you have to be very careful about the first and the last row. So here is a common example. So let's say that you have this accumulator functionality in Halo 2. Let's say this is a chip, and you place constraints as in selector times 10 times accumulator plus the next value. The primes are like next row. The next row of values minus the next row of accumulators is equal to 0. And for example, let's say here, since the selector here is 1, selector here is 1, you see that 5 times 10 plus the next value of 8 is equal to 58, which is the next row of accumulator. So this looks to be a sound implementation of accumulation, base 10 accumulator something. But in fact, this is actually not correct because there is one missing constraint, which is that on the first row, the value and accumulator has to be the same. So this is so in a way, this is like a mathematical induction kind of problem. So if you do a mathematical induction, you have a base case, you prove the base case is correct, and then you prove that if you have statement that's correct for like n, then you have a statement that's correct for n plus 1. But so similar to that, this vulnerability I just showcased here is kind of like missing the proof of a base case. So you forgot to prove that the first row's value and first row's accumulator are the same. And this is very common. And one thing to be aware of is that this is about like the first row of the region. So this is on the first row of the region. But sometimes it's very important to check whether the last row of a region should have additional checks regarding soundness. So first rows and last rows are very like easy places to like miss a bug. So you have to watch out for that. This was like very if you read a scroll audit report, there was some cases like this there. And finally, on this is more of a MISC thing because it's not really this is not really a circuit bug, but there are plenty of attacks on the cryptographical backend and some other stuff. So for example, more of the difficult cryptography related vulnerabilities that are that surfaced recently is the frozen heart bug by Trail of Bits, which is which is about like weak Piaget on the prover side. There's like some common cryptography related bugs like weak randomness. The prover could lose zero knowledge by not placing sufficient amount of blinding rows, and there are also some weird ones like compiler optimizations where like unused public inputs are optimized out, which leads to like malleability. And so in conclusion, so there's like a bunch of possible attack vectors. So the conclusion I want to make here is that for each of these attack vectors, there's like there's an underlying reason for it. For example, like as I mentioned before, like the variable length objects and the handling of boundary and transition constraints, these are all fundamentally based because of the fundamental fact that Plonkish supports fixed rectangular boards only. And same for Fiat-Shamir and like these other assumption handling and so on. So all in all, the final thing I want to mention about is that the mathematical prerequisite for ZKP security and like how much cryptography / math is actually needed. And my answer for this is that you have to see like how much cryptography / math is actually exposed to the surface. And the answer for like how much math you need will be basically enough math to understand this. Yeah. So let's just take a look at some examples. I don't know how to phrase it in English. So let's just look at some examples. So first, in the first case, let's just say that like you have to audit like the entire prover and entire verifier logic. So in that case, you have to like know the entirety down to the paper level. So if you have to like audit a Fry implementation, you have to like audit a complete like snark prover, like the cryptographical backend of it, then you have to like know everything down to the paper level, and you have to understand like why your protocol is sound. You have to understand why the protocol has zero knowledge and so on, down to the mathematical proof level. But in the case though, the most common case for now, which is you have to audit the usual Halo 2 circuit, then you have to know math/cryptography enough to first know the relevant math for the application specs. So if you're auditing ECDSA implementation in ZKP, then you have to know ECDSA very well. And if there are chips for mathematical operations, such as like comparing, range checking, bitwise decomposition, like addition and so on, and or like wrong field arithmetic and so on, you need to be able to, given a ZKP friendly implementation in Halo 2, you need to be mathematically good enough to prove both soundness and completeness for the circuit implementation. And since Halo 2 exposes like first phase and second phase APIs directly to the like circuit writer, you also have to have a strong intuitive understanding of Fiat-Shamir and what should be first phase and second phase and so on. And obviously you have to have a strong understanding of the underlying library here, Halo 2. So these are the mathematical prerequisites you need. So one point here is that, for example, if you are not proving, I don't know, if you're not proving pairings in circuit, you don't really need to know pairings that well, I think, in my opinion. And moving on to case 3, sometimes what could happen is that you have to audit a Halo 2 circuit, but all mathy things are already audited. So for example, if there's like a very common library for things like additions, like things like unit 64 things, or things like bitwise decompositions and all those like fundamental mathematical blocks, then this part, and maybe if there's like limited number of use cases for Fiat-Shamir, like for example the concat proof that I just showed above, and all those relevant circuits that actually explicitly use Fiat-Shamir are all like fixed as libraries and all out of scope, then this part and this part of the like mathematical prerequisites are gone or are removed. So what the things that will be left would be the first thing, the relevant math for the application specs, and strong understanding of the underlying DSL/library. Again, here Halo 2. So since we remove these two, now like the remaining things are like pretty I don't know how to say this, that it's obvious that these two are already needed. Like you would need these two regardless of like what field you are in. Either this is the KP or smart contract security or like any other security, you would need these two anyway. So for example, going even further, let's say that the ZKP related like project is in a like DSL or for example, maybe even a ZK VM that does all the ZKP stuff under the hood, then you would still need to know like the relevant math for the application specs, and you would still need a strong understanding of a underlying DSL/library. And I mean, like even in a smart contract, you would need to know the relevant math for the application specs. So if you're auditing DeFi, you have to know like the rounding issues and so on, and like all the like units of V3 math and so on. And you would also need a strong understanding of the underlying library/code base, which is Solidity. So like this is all a pattern. So in the end game, so in my opinion, in the final end game, if a strong DSL or a strong library or a strong VM comes out with for a ZKP circuit writing, comes with a library that handles all common mathematical functions and all common tricks as a fixed library, which is like audited somewhere else, and then all cryptographic tricks are done under the hood. So the end user so that the quote unquote common circuit writer doesn't have to like deal with this themselves. Then if this kind of era comes, then ZKP security math will be like much easier than it is right now. I think it could be like just easier than DeFi related security math, I think. So in that era, I guess that compiler related stuff, because you're dealing with a DSL that handles the ZKP things under the hood, compiler related stuff could be much more important. And I think the quote unquote fundamental security skills which carry over from ZKP to DeFi to any other smart contract or even nodes, and the quote unquote adversarial mindset, which is common for all these security topics, will be much more important. So math might not be the most important thing that's that's needed for ZKP security if this era comes, and I think this era will come sooner or later. So yeah, so math might not be that important after all. Yeah. So that's the stuff I want to talk about. Are there any questions?
Yeah, thank you. Yeah, we got some questions. Do you want me to read the question, or maybe you can read for
I
the
see.
recording?
I
But it's
see.
better, I think, to read for everyone to.
Sure, yeah. Okay, should I read it?
Or do you want me to read?
Okay, I'll read it. So Nullity asks, to accelerate the painfully slow ZK infra, we see a lot of ZK acceleration libraries coming up based on GPUs and FPGAs. I'm wondering where this fits in the ZK stack and how much of an issue would it be when there's bugs in ZK acceleration libraries. Do you think unaudited ZK acceleration libraries would affect soundness of the proof system? Well, it depends on like how much the acceleration is being used, like where the acceleration is being used and how it is being used might be one of the key aspects of answering this question. Like, let's see. If the verifier uses acceleration, then if there are like mistakes in the acceleration code, then like incorrect evaluations would lead to like the quote unquote accelerated verifier accepting like incorrect proofs. So maybe that's a possible issue. But in general, I'm not like that knowledgeable regarding like GPUs and FPGAs to like confidently answer this question. But yeah. Mm, yeah, not sure. Not really sure about it. Yeah. Hmm.
I think if the only problem is in the acceleration software, then the proof shouldn't compute. So let's say
Yeah.
you have you have a ZK snark which is 100% complete and sound, but
Mhm.
then you paralyzed it. If there is something wrong in the parallelization,
Right.
then
It
the
could lead
proof which
to
the verifier is going to catch that, assuming that's the only problem. The only problem is that they haven't made implementation of parallelization. Yeah.
right. So maybe like if you have like I don't know incorrectly written the like acceleration code and it doesn't satisfy completeness, then it could be like an interesting take. Like for example, the acceleration works for a certain set of inputs, but on some very like specific and niche set of inputs, the acceleration fails. And in that case, there could be some like completeness issues, I guess. Yeah, interested to see like where the like acceleration thing comes, like the hardware acceleration thing comes into like the security landscape. It will be very interesting. Yeah.
In terms of randomness, RK,
Mm-hmm.
to what extent things like primitives like Viet-Shamir, to what extent are they actually susceptible to weak random number generations? Because from what I see, they shouldn't. The random number generation shouldn't factor into it because the randoms is coming from the hashing
Mm-hmm.
of the from integrating the result into the hash that
Mm-hmm.
is used in by the prover to compute the randomness or the gamma, right? Um, so I'm wondering where like randomness, like pesky randomness problem factor in. Is it in these primitive uh, or is it like somewhere else, like the RNG used during trusted setup and things like that?
Well, for Fiat trick, on like attack 7-2, it was more about just using. Uh, okay, let me be like more explicit in like potential like attacks slash mistakes that could happen. Uh, First there's like obviously the prover using the like wrong Fiat, which is the descripted like below the frozen heart thing. Uh, there's also cases where if you're like not like direct quote unquote directly using Fiat in your circuits and you're just like just handling first phase and second phase in Halo 2, one mistake that can happen is that the 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 circuit writer could like assign a column as second phase when it should be first phase and something like that. That could definitely happen. And on sometimes uh to like use stuff like RLC, the circuit writer will explicitly compute gamma for the RLC stuff as a hash, but forget to like add in variables that need to be added in when doing the hash in order to do a safe Yashamir. So all of those all of those are possible attack examples. And yeah, and like obviously if you make a mistake on Fiat Shamir, uh the 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 soundness breaks. And uh for the LLL related stuff, this is for like cases where like the variables that are RLC'd have a specified range. For example, like if A, B, and C are just like field elements, like they're just FP, then LLL is not like lattice attacks are not needed. But for example, if A, B, and C are like constrained to be like byte array elements, then you would have like it is non-trivial to find a, let's say if you have incorrect Fiat like the gamma is equal to h a hash of A and B, then it is not trivial to find a byte array C that satisfies this thing. Uh, with Together with the fact that like C is not the concatenation of A and B. So for that, you would actually need to use some kind of a lattice related attack to find the like possible like like to showcase that soundness is broken. So lattice attacks are pretty nice for that. Pretty I don't know, useful for that. Yeah. And another question I see here is that is there any dynamic lookup exploit example? There is a dynamic lookup related, uh, I think it was issue slash pull request on one of the like public open source like ZK Vim code, but I haven't really seen a like actual example from a audit report or something like that. Um, Dynamic lookup itself is quite rare, so yeah. Like I think I haven't seen. Wait, I don't know. I'm not too sure, but yeah, I don't have an example in mind right now. But it has been discussed in like ZKP security related circles. Let me try to find a link to that.
Maybe you can post it in the in
Discord.
Discord now.
Yeah.
I don't know if there are any more questions from the audience. I'm wondering also, like in your approach, like for the audit, like you are mostly taking manual approach, like are you aware of like any tooling that can be used like for zero knowledge?
Regarding tooling, I'm not really like I don't really know much tooling to be honest. Uh, it's something that the ZKP world has to, I don't know, do better on, I guess. Like there are many approaches regarding tooling out there in ZKP security world, there's like ECNI and there's like people who do formal verification and so on. But personally, I don't really know much about them, to be honest.
Yeah. Yeah, it seems like there are some tools, but they're not really like universal, like, or not
Right.
very well developed, like, so yeah.
Yeah.
Yeah, tooling is very immature, and that's one of the reasons why we are encouraging everyone to work on them or come up with ideas in tooling and things like that. It's part of like the bounties we talked about. So our case, since we have you here and you have audited before, if there was a tool that you wish you had,
Mhm.
or you think should be out there, but it's not, feel free to tell us and we'll see if we can work on them.
Right. One of the like things that are, I think it's present in ECNI, and it's also like present in just smart contract security, is something like interval arithmetic, quote unquote interval arithmetic, where like, for example, if there's like let's say B0 to Bn minus 1, which are known to be 0 to 0, either 0 or 1, then you can write A is sum of bi to the power bi times 2 to the power of I, and then uh if there's like a like a supporter in the back end that automatically converts A is within 0 to 2 to the power of n, it would be pretty helpful. Like it would this something like this could like be very helpful to, for example, keep track of which variables are already known to be bits. And like if A and B are input as, bits, and then you compute like A XOR B, then it comes out known to be bits. And like the linter or something in the back tells you that, oh yeah, this is actually, bits, and help, help with the whole range check thing. That would be pretty nice. Uh, but and like this kind of thing exists in the like smart contract security world. I think it was actually Nascent that developed it. I'm not sure, but I don't remember the name of it.
Parameter, no? You're referring?
Yeah, right, like the parameter thingy. Yeah,
Yeah,
is it pyrometer or
parameter, yeah.
yeah, right, that thing. Yeah, sounds pretty useful.
Yeah. For boundary strip, yeah.
Yeah.
Also, do you have like any good like examples like for documentation? You said like that you were referring that it's important like to document something. Like I'm wondering if you know good examples like of documentation for zero knowledge protocols.
So do you want me to talk about like examples regarding documentations?
If you have some.
Oh yeah, so like one of the very like more common things is that, like as I mentioned earlier, some of the main assumptions that should be written but not documented well are the like range checks in regarding inputs. So if a chip A takes A and B and assumes that A and B are bytes, uh, but doesn't document that A this assumption exists, then some other chip B uses chip A and doesn't and B doesn't check, and chip B doesn't check that the inputs are bytes, and so on and so on, and then like it just crashes at the end because like nobody's just checking that the inputs are bytes. And
Yeah.
no one knows like where this should be actually done. Like another like thing, for example, is that uh yeah, like there are like many chips out there that, oh, if inputs are bytes, or let's say inputs are bits, then the output is a bit. And so if you run computations over them, if you know that the starting point the starting variables are bits or bytes or range checked or whatever, or satisfy whatever assumptions you need to check, then it would be all fine. But nobody checks that the starting variables are safe. So like very very bad stuff happens, and then it just gets all blown up in the end.
Yeah, it's like more documentation for chips. Yeah, like
Yeah, it should be like very very clearly documented that which chips have an assumption on it and which chips explicitly check the assumption on it, and that all all relevant computations and usage of such chips go through at some point the range check or some validation on the assumption.
mhm.
And of
And
course,
what
as I
would
mentioned, sorry, of course, one thing that I mentioned here is that while it would be best if like all chips, like chip A, B, C, and every single one of them just check the range check by themselves, like all chips to do the range checks by themselves, but you can't do that because range checks are expensive and you can't afford to do that, unfortunately.
Mhm.
Yeah.
Yeah, and I recall that you have found like more than 50 zero knowledge vulnerabilities, right? So I'm wondering like what was the most common case
The
that you've
most
seen?
common case for me is like one thing that like I want to like assure is that like only a small number of bugs relate to are mathematically advanced. Like most bugs aren't that mathematically advanced at all. I think attack one is very important. There's a lot of mistakes in attack one, in like just simple specification issues. And another very common thing is this boundary and transition. Like if you're going to like compute a running sum of this is it. Like this issue happens quite a lot. Like if you are trying to compute a running sum, if you're going to compute like an accumulator over like various rows, you have to always be careful that the first row and the last row are handled properly. And this mistake comes up a lot in circuits, even though it's like very like not mathematically advanced. So it's I recommend like everyone to like check if there's like a region, if there's a chip and there's a region associated with it, check the first row and the last row, especially if the uh yeah, yeah. So this is very common, so check it.
Yeah, thank you.
And
I don't know if we have more questions or we can wrap it up.
yeah, I think we can wrap it up. Thanks for having me. Like the talk was very like rushed. So I hope like people understood most parts of it. I'll be very happy to like answer any questions like even after this talk. Could just like give me any questions on Discord and I'll be very happy to like explain.
Yeah, thank you very much for this very hands-on presentation. Was great to see your findings like and potential vector attacks. Yeah, we stay connected on Discord. Feel free to post anything like, and we will be looking to ask you some questions maybe.
Yeah.
And yeah, have a good day, evening, night, everyone.
8 p.m. here. Yeah.
Yeah.
Thanks, okay. That was great.
Thank you.
Thank you.
Bye-bye.
Bye.